Thank you. Thank you all organizers to inviting me. It's a pleasure to be here. Not personally, but yeah, Symplectic Zoominar is amazing. So I will talk about a work joint with Vinicius Ramos, which was my PhD advisor, and Alejandro Vicente, which is another Vini student. And I'm going to start with recalling the Gromov's nonsqueezing theorem, which we all know by heart. So consider the open ball in R2N, and then a symplectic cylinder, meaning that you consider a symplectic base, like a symplectic plan as base, like Q1, Q1, Q1. And then Gromov's nonsqueezing theorem says that the ball symplectically embeds in the symplectic cylinder, considering the standard symplectic structure in R2N, if and only if the ball is really contained in the cylinder. So the inclusion is the optimal embedding that you can do. This is the standard picture. And the picture helps us to motivate a nice exercise to prove that you can use the unbounded directions on cylinder to produce like volume preserving embeddings. So symplectic embeddings from Gromov nonsqueezing theorem are different from volume preserving embeddings. And in fact, it gives rise to invariants, global invariants that are not like volume. So in fact, we have a family of invariants, and this is one of the first examples. This family is called symplectic capacity. So a symplectic capacity assigns to a given symplectic manifold a non-negative number that can be infinity, and this satisfies three properties, nice properties. The first one is the monotonicity. So if a symplectic manifold embeds into another, the capacity of the first manifold, the embedded one, is lower than or equal to the capacity of the target one. And then this gives obstruction to symplectic embedding problems. The second property is the conformality. So it means that the capacity scales well when you multiply the symplectic form by a real number. And then we have the non-triviality that excludes, for instance, the zero function or any volume variation. So the capacity of the ball, standard ball, is positive, and the capacity of a symplectic cylinder is finite. Sometimes we add another property called the normalization condition that asks that the ball of the cylinder has the same capacity, and this is equals to pi r squared, the area of the disk. Okay, so these are symplectic capacities. And here are some examples. The first example is the Gromov width. So this measures the biggest ball that you can symplectic embed into a given symplectic manifold. So more precisely, this is supremum of pi r squared when you consider all the embeddings from the ball of radius r into your symplectic manifold. By Gromov nonsqueezing theorem, this satisfies the non-triviality condition. The other conditions are more trivial to check. So this is the first example of a symplectic capacity, and in fact, it's normalized. Other examples, nowadays we have several examples. So I'm going to mention some examples. The first two are given by calculus of variation. So Eckland-Hofer capacity is Hofer's and the capacity. The other two, the turbo capacity and S1 equivalent symplectic homology capacities, or just Guth-Hutchins capacity, are capacities that come from symplectic homology theory, like the algebraic structure. And we also have the ECH capacities defined by Hutchins, but these only work in dimension 4. These capacities with a K here, an index like the Eckland-Hofer, Guth-Hutchins, and ECH, means that we have a whole sequence of symplectic capacities, and even the first ECH capacity is normalized. I'm gonna show you two examples because it will appear in our result. So the first example is an ellipsoid. We consider ellipsoid with this pi here in such a way that this ellipsoid has volume A times B over 2, where A and B are these parameters. And for this manifold, the sequence is really interesting, like combinatorially. You consider all the linear combinations of parameters A and B with weights being non-negative integer numbers. So you organize this in non-decreasing order, and this is the whole sequence. So this is the sequence for the ellipsoid. And in particular, when you consider the parameters being the same, you have a ball, but with the pi here. We used to call this ball ball of capacity A, because the normalized capacity is equals to A. The radius is square root of A over pi. And then we have this beautiful sequence here. So the first value is 0, then you have A 2 times, then 2A 3 times, 3A 4 times, and so on. So it's very symmetric. And the other example, so this example was computed by Hutchins, and the other example is the manifold, the main subject of this talk. So the disk cotangent models of Zoll spheres of revolution. Here, sphere of revolution means a smooth sphere in R3, but it's invariant through a rotation around a fixed axis. You can fix like the z-axis and consider spheres like this when you rotate smooth curves with some properties at the endpoints. And it's Zoll, as always, like if our geodesic rays are closed and has the same prime length. Here the metric is induced by Euclidean metric in R3. And then we can consider this cotangent bundle, which is the manifold consisting of all the covectors with norm lower than one. Yeah. Okay. Here I consider on purpose the open manifold. Okay. So for this case, whenever it's Zoll, we can compute the whole sequence of ECH capacities. And the nice thing is this is distinguished to the sequence of the sequence for the ball. So consider this beautiful L being the length of any simple closed geodesic on the sphere. And then the sequence is exactly the even multiples that appears in the sequence for the ball. So it's 2L 3 times, 4L 5 times, 6L 7 times. And it's related to the fact that you need to go twice a simple geodesic to obtain a null homologous orbit in the RP3, which is the boundary of this cotangent bundle. Okay, so these are the two examples which go up here. And what is our strategy to compute the Gromov width for some examples? We follow two steps. We obtain the obstructions, like from above by the capacities, by the monotoricity, and then we construct or prove the existence of symplectic embeddings to get another bound. And the dream is when you can get the same bound and you compute the Gromov width. So for the other direction, we use toric domains. Toric domains are examples of symplectic manifolds that we can understand like in a better way, symplectic embedding problems, mostly due to embedded cohomology. So given a region in the first quadrant of the plane, omega, we consider the pre-image by the moment map of standard toric action in situ. So more precisely, X omega is the set of Z1, Z2 in situ, so that the pi normal Z1 square, pi normal Z2 square lives inside the region that you choose. So every manifold of this type we call a 4-dimensional toric domain. And here are some examples. The ellipsoid. So the ellipsoid corresponds to this right triangle, and the area is exactly A times B over 2. So this is the volume of the ellipsoid. And due to this pi, we consider in the definition. And then we have polydiscs, which are exactly product of disks in complex planes. So you have this disk of area A and this disk of area B, and you consider the product. So the image is exactly the rectangle. These are the two examples that will appear today. And what is our idea? Is try to follow Vini's strategy and find some toric domains in disguise. So it's well known that the geodesic flow on spheres of revolution is integrable. So the idea is to use this. Consider here now a sphere of revolution, but only with a unique equator. Here, an equator means if you consider the profile curve, like the intersection of y is equal to 0 plane, and the positive part. So this is a curve like this, and we have critical points of this distance, or you can just consider this being a graph of a function, and every critical point of this function gives rise to an equator. So equator are geodesics, and they are given by that description. But now we are just consider unique equator. So you can consider like ellipsoids, so part of ellipse, but you can also consider like a drop, having just this down equator here. And it's a nice exercise to prove that every Zoll sphere of evolution just have a unique equator. Okay, so this is our first hypothesis. And then we can find a toric domain. So this is an existence theorem. There exists a toric domain that if you consider the punctured sphere, so you have the whole sphere, we remove the north pole, which is this highest point here, and consider the disk cotangent bond of this submanifold. So this is symplectomorphic to the interior of a toric domain. This is our result. And in fact, we can describe this region in such a nice way. This omega S is a region given by bounded by the coordinate axis and by a parametrized curve related to the parametrization of the profile curve. So we have a nice description. And if it's Zoll, in fact, we can go beyond, go further, and prove that this region is a square of size L, where L is again the length of any simple closed geodesic. So if you have a Zoll sphere of evolution and consider the punctured sphere and look at the whole disk cotangent bundle, this is symplectomorphic to the interior of a polydisk. This is our first result. The proof ideas is exactly following Vinicius strategy. So we consider the integrable system given by the energy and angular momentum, and then we perturb with a suitable smooth function, potential, just depending on the basis, Q. And then applying the Arnold-Liouville theorem for every epsilon, you have these nested domains, which are the pre-image of the interval 0, 1. And they are symplectomorphic to toric domains by action angle coordinates. But in fact, these toric domains are again nested. So you can use extension theorems to obtain, in the limit, a symplectomorphism. And in fact, you can parameterize the curve letting epsilon goes to 0. So you have the description of the curve that bounds the region. This is the idea. And for Zoll, we have the polydisk. But there's another nice example, which is ellipsoids of revolution. And for that case, we just consider ABC real numbers and the standard ellipsoid. So the set defined by this equation in R3. And in that case, the thing is, the profile curve is parameterized by elliptic integrals because you are integrating the arc length of ellipses. So in this case, we can manipulate the integral that is given by the action angle coordinates. And then using Matemática, Wolf from Matemática, we can plot these regions and they are awesome. Obviously, I'm considering the case of ellipsoids being of revolution. So it's exactly when two of the parameters ABC are equal, and we can normalize like the two first being is equal to 1. So the unique parameter which is free is C. And then we have these 3 types of toric domains. So whenever C is lower than 1, which means that the ellipsoid is more flattened, we call this oblate ellipsoid. We have this first picture, which is a picture of a region which is not concave nor convex. So it's a nice example for a curious toric domain. Whenever C is equal to 1, we are on the ground sphere case, and this is all. So this must be square with size 2 pi, because it's the length of any great circle on the ground sphere. And whenever C is bigger than 1, we have this third picture, which looks like a sphere. And this is exactly a convex toric domain, a weakly convex toric domain, meaning that this region here is convex. So we have these 3 situations. The last one corresponds to prolate ellipsoids, which is an elongated ellipsoid that way. Okay. Using these toric domains, we were able to compute the Gromov width. So these toric domains we can use to produce balls inside them and gives lower bound to Gromov width of the disk cotangent bond of ellipsoids. And on the other hand, we can use estimates on these H capacities and gives the obstruction. So here follows the theorem. We compute the Gromov width of the disk cotangent bond of the ellipsoid with parameters 1, 1, C. And this has a nice behavior. I prefer to explain this using the picture that I put here, which is the graph of the function, which assigns for each parameter C the Gromov width that we want to compute. So I don't know if you can see my arrow. I'm shaking my mouse here, but yeah, we have this nice behavior from 0 to 1/2. This is given by elliptic integrals. This alpha of C is exactly the length of a closed geodesics that only exists 4 parameters below 1/2. And this geodesic oscillates around the equator. And in fact, when C is equal to 1/2, this geodesic collapses into the equator. So in that case, from 1/2 to 1, we have this Gromov width constant equal to 2 pi, which is the length of the equator. But from 1 to a critical value, which we call C0, this corresponds to the length of a meridian. So it seems to be a linear here in the picture, but it's not linear. It's again given by elliptic integrals, because this is the meridian, the length of these ellipses. And C0 is exactly the value when the meridian has length 4 pi. So whenever you hit this point where the meridian measure 4 pi, you have now another behavior. And from now on, the function, the Gromov width is, or to infinity equals to 4 pi. So this is constant, equals to twice the equator. This should not be that surprise, because, as I said, you need to go twice to of a geodesic to obtain a null homologous over its set. And here we use ECH capacities, and 4 pi is exactly the action of twice the equator, because we fix the equator with length 2 pi. Okay, so the idea is exactly this, using the toric domains to prove the existence of symplectic embeddings, and it gives lower bounds, and then estimates in ECH capacities to give higher bounds. And we can prove that this coincides in this case, and it gives the whole description of this nice function. The other result is the Gromov width for the Zoll case. So consider a Zoll sphere of evolution with this beautiful L being the length of any simple closed geodesic, and then the Gromov width is exactly this length. So we did prove in a previous work for the round sphere this example, and in fact, for the round sphere, if you consider the disk cotangent bond of a hemisphere, this is the ball of size 2 pi. But more generally, for Zoll sphere of evolution, we can prove that this is the Gromov width. It's not true for every Zoll manifold that this is the hemisphere corresponds to this ball, but we can use this theorem that we prove that if you remove the North Pole, this is the polydisk. So the ball of size L is contained in the polydisk, obviously, because the right triangle is contained in the rectangle. But this is symplectomorphic to this submanifold, the disk cotangent bond of the punctured sphere, and hence we have this bounded, this lower bound from the Gromov width. On the other hand, if you have any embedding of a ball of capacity size A into the disk cotangent bond, the whole disk cotangent bond, we can use monotonicity of ECH capacities, and the third ECH capacity of the ball is 2 times A, and the third ECH capacity of the disk cotangent bond is 2 times L, the length of the geodesic. And then A must be lower than L and lower than or equal. And then we can pass the supremo and conclude this another bound. And so it coincides, and the Gromov width must be equal to this length. That's all that I plan to talk about. It's 20 minutes. I don't know if I rush, but I'll stop here.
Thanks, Brian. That was a great talk. Any questions from the audience?
I have a question. In the last theorem, when you had, yes, for the Zoll things. So do you have an example, an interesting example of, so you go through this toric domain, right? Or it's always going to be the, oh yes, it's always going to be the polydisk. Okay, thanks. Sorry.
I would like to ask a question. Does this toric domain and identification with the disk cotangent bundle, does it send action 0 to the 0 section of the disk cotangent bundle?
Yeah.
Okay, thanks. So you also get the estimate for the relative Gromov width, right? It should
Probably.
be the...
I'm not sure I know what is the relative Gromov width that you're saying, but yeah, I think it's
relative to the 0
you're
section.
comparing to the 0 section. Yeah.
Yeah, okay.
It's in the 0 section. Yeah. Actually, if you apply the Arnold-Liouville theorem just to the integrable system of geodesic flow, you obtain something like you have the axis. I'm sorry, I can't draw because my connection is really unstable and I won't use my tablet, so my iPad. So you have this figure, like you have a toric domain above, another toric domain below, and you have a measure zero subset, which corresponds to angular momentum equal to 0 and 2 equators. So these are the critical points. And in fact, you have this decomposition of 2 toric domains, which are symplectomorphic to each other, and another subset, which is a measure zero subset. And you can obtain this without perturbing the system. So in that case, you can estimate the Gromov width of any Zoll spherical evolution. This is at least the minimum length of an equator, because you can use Ferrion trick to fit a triangle inside of one of these regions that I mentioned.
Okay, thanks.
Did you try to make calculations for the sphere, for the torus of revolution?
Actually, I didn't. I just used the spheres of evolution, but yeah, it could be interesting to try this. But my main tool is like ECH capacities, and for the torus, we have the boundary of the disk cotangent model of the torus is T3, right? So we can use Sullivan, Hudson-Sullivan theorem. Yeah, it would be nice to try. Thank you.
I think it's possible, like generalizing toric domains to things that are, but it's not going to work with toric domains, but with other things, I think it's possible.
Right, because on tori, there is another class of integrable system, which is called Liouville systems, which is a kind of generalization of surfaces of revolution. And what happens there, not clear at all. So it's, and I think it's interesting to understand how integrability of the boundary, but already kind of non-trivial integrability, influences all the symplectic invariant.
Yeah, thank you for your comment. I'm gonna search about this. Yeah.
Any more questions or comments? Okay, so then we thank Brian again. So thanks a lot, Brian, for the talk.